Thanks for watching. And by popular demand, today I want to evaluate the integral of sine of x. So I got lots of requests for this, and the whole time I'm like, no, I can't do it. It's impossible. But guess what? It is actually possible. If you expand your mind and accept special functions and series. Because it turns out this function, just like e of negative x squared, you cannot express the integral in terms of elementary functions. But, as I said, we can somehow express it as a series. And in fact, when you see sine, you may think Fourier series. And this is true. It turns out sine of x has a particularly nice Fourier series. So step one. Let's expand sine of x, your dog, as a Fourier series. So somehow you can write this as a sum from n from 1 to infinity of bn sine of nx on the intervals minus pi, comma pi. And what is the bn? Notice this is a Fourier sine series, and we have some very nice formulas for the Fourier sine coefficients. Simply, bn, it's 2 over pi, integral from 0 to pi of sine of x, sine of nx dx. So surprisingly, even though this integral is more complicated than the other one, turns out this one is a bit easier to analyze. Because first of all, here n can be even or odd, but it turns out the even terms will all disappear. So this Fourier series actually sine of odd n times x. And why is that? So note, if n is even, I can't even, then n is of the form 2k, and then b2k, so bn, is simply 2 over pi, integral from 0 to pi, sine of x, sine of 2kx dx. And then it turns out there's a nice symmetry involved here. And in fact, let's explore the symmetry by using a u substitution. So simply let u be pi minus x. So in particular, reversing this, x is pi minus u. And let's see what this integral becomes. 2 over pi. Now, pi minus 0, that's pi. Pi minus pi, that's 0. Lots of pi's. It's very delicious. And then we get sine of x is pi minus u. Sine of 2kx, which is 2k times pi minus, 2k times pi minus 2ku. So it's basically sine of 2 pi k minus 2ku. And then lastly, dx is minus du. Which is good, because you see this minus du, it rectifies this integral. Because notice this is in the wrong order, but because of the minus, we get the right order. So this will be integral. So 2 over pi. Integral from 0 to pi. Alright, now sine of pi minus u, you can simplify this. So sine of pi minus u by the addition formula for sine. So that's sine of pi cosine of minus u, and then plus cosine of pi sine of minus u. Sine of pi, that's 0, that disappears. Cosine of pi, that's minus 1. And this is minus sine of u. So in the end, you get sine of u. So this becomes sine of sine of u. And now more interesting, this term here, well, if you add multiples of 2 pi to sine, you don't get anything. And this is precisely, again, why we assumed n is even. So this term will be sine of minus 2ku in du. And lastly, this minus, you can just pull it out because sine is an odd function. But now just compare both terms. Here we have 2 over pi, the integral with respect to x, and minus 2 over pi, the same integral with respect to u. So because x and u are dummy variables, this becomes precisely minus 2 over pi b2k. And so what do we get? Oh, yes, sorry, it's precisely minus b2k. And what do we get? b2k is minus b2k, so everything's okay. So b2k is 0. In other words, all the even terms in this series, they vanish, and therefore this series is just an odd sine series. Just interesting because sine series have to do with odd functions, and now we just consider the odd terms. So step 2. So what do we get? Sine of x is just the sum over odd n. So n from 1 to infinity of n odd of bn sine of nx. Alright, so from now on, you just consider n odd. That is, n is 2k plus 1. Right. And here's a trick. So it's kind of weird to motivate, but it turns out the function I'll write down, it's a very standard function. So consider the following. I don't want to reveal the secret, but if you know the function I'm talking about, you will recognize this. Consider, in this case, cosine of nx minus sine of x. So in other words, cosine of the difference between sine and the function nx. And it turns out if you expand this, you have our sine of nx function. So because then this becomes, by the addition law of cosine nx and cosine of minus sine of x minus the same thing as sine of nx, sine of minus sine of x. And well, cosine is an even function, so you get cosine of nx and then cosine of sine of x. And then sine is an odd function, so this goes out and you get minus minus, which is plus, if you want, sine of x, sine of nx. But this is really good because remember the definition of Bn, you just multiply sine of x with sine of nx and you integrate. So what we get then is simply as follows. We then get, so again, what is Bn? By definition of the Fourier coefficient, that's 2 over pi, integral from 0 to pi, sine of x, sine of nx, dx. But we just saw that this term you can solve in terms of this and this. So really what this becomes, it's 2 over pi, integral from 0 to pi, cosine of nx minus sine of x and dx. And then minus the other one, 2 over pi, integral from 0 to pi cosine of sine of x, if you want, and then sine of n, I guess cosine of nx. Now, and dx. No, never forget the dx, as Black Pen, Red Pen says. It's like driving without a seatbelt, which is, you should drive with a seatbelt. All right, and here's the big revelation. Because as I said, the integral can be written as terms of special functions. Well, it turns out this term, like this whole term, it's simply what's called the Bessel function of first order at 1. So this, or I guess 2 over that. And this is what's called 2jn of 1, where jenning in the block, so gny, it's simply 1 over pi integral from 0 to pi cosine of nx minus y sine of x dx. So notice in particular here, the coefficient of sine is 1, so it becomes jn of 1. And again, this is a special function, and it makes sense because the integral of sine of x, which we haven't evaluated yet, doesn't have a closed form, but it turns out you can write this in terms of those special functions. And this is a function that arises a lot in physics and differential equations. And at the end, I'll give you some cute properties. But this is already a small victory. We can write our sine coefficient in terms of this known function and this junk. And now let's just show that this junk is 0. Because it turns out this other thing is irrelevant, which is good. It would mean that Bn, our coefficient, it's 2 times this Bessel function of the first kind. All right. So only let's just show it's 0. Then let's integrate, and then we're done. So step 3. So let's show that this is true. Integral from 0 to pi, a cosine of sine of x, cosine of nx dx equals 0. And for this, we would like to explore a nice kind of symmetry, and also using the fact that n is odd. So this would not quite work if n is even, but it's good. We know that n is odd. And here, let's explore the symmetry around pi over 2. So this time, let u be pi over 2 minus x, and then at 0 we get pi over 2. At pi, we get minus pi over 2. So pi over 2 minus pi, which is minus pi over 2. And then we get cosine of sine of pi over 2 minus u. And then cosine of n pi over 2 minus u. And again, a minus du. Which is good because it rectifies the flaw in the integral. Because this term and this term. They simplify, and then what we're left with, so very important, we have the integral from minus pi over 2 to pi over 2. And then cosine of sine, so sine of pi over 2 minus u, it's cosine of u. So we have cosine of u and cosine of n pi over 2 minus nu du. And now let's see how we can simplify that other term. Because so far it's not obvious that it's 0. And as I said, so far we haven't used the fact that n is odd yet. But now, note. Cosine of n pi over 2 minus nu, that is cosine of 2k plus 1 pi over 2 minus nu, and that is cosine of, if you want, k pi plus pi over 2 minus nu, and that is cosine of pi over 2 plus k pi minus nu, and that is cosine of pi over 2 minus nu minus k pi. And again, if n were even, we wouldn't have this factor of pi over 2 here, but the nice thing is, this is just a sine of nu minus k pi. And we can expand this with the sine, addition formula. So this is sine of nu cosine of minus k pi plus cosine of nu sine of minus k pi. But sine at multiples of pi is just 0. So what you're left with, and cosine is even, so this is sine of nu cosine of k pi, and this is sine of nu minus 1 to the k. And why is this important? Because this term becomes minus pi over 2 to pi over 2 cosine of cosine u, and then sine of nu, and then minus 1 to the k du. But notice, this function is even, this function is odd, so this whole shebang is odd. And an integral of an odd function over a symmetric interval around 0 is just 0. So indeed, the junk term that we didn't want is just 0. And therefore, we can conclude all right. Therefore, we can now conclude, what is Bn? So last step, Bn. We saw that if n is even, it's 0. And if n is odd, it's 2 times the Bessel function of the first kind. So in other words, what we have is simply b of 2k plus 1, it's 2 times j 2k plus 1 at 1. And then, let's see what our function is. So notice we still haven't integrated sine of x, but we'll do this very soon, I promise. Because sine of x, we express it as a series now. Sum from n from 1 to infinity, bn sine of mx. But remember, at even terms this is 0, so this is really the sum, if you want, from k from 0 to infinity, b 2k plus 1 sine of 2k plus 1 x, and this is just sum from k from 0 to infinity of 2 times j 2k plus 1 at 1 sine of 2k plus 1 x dx. No, dx, not yet, soon. So we have this. And lastly, how do we get our integral? Just integrate. So take this, integral dx equals this, integral dx. Assume we can interchange the sum and the integral, which I think is justified here because those terms, they go to 0 very quickly, so it's like a uniformly convergent series, and those can be integrated term by term. So what you're left with is the sum from k from 0 to infinity of 2k plus 1 at 1 times the antiderivative of sine of 2k plus 1 x dx. And then what this becomes, so an antiderivative of this is minus cosine of 2k plus 1 x over 2k plus 1 plus some constant. So in the end, what we get, we have a minus here and a 2 here. So minus 2 sum from k from 0 to infinity of those numbers, j 2k plus 1 of 1 over 2k plus 1 cosine of 2k plus 1 x plus a constant. And we're done. This is your integral. So the integral of sine of x equals to this weird sum. And as I said, unfortunately, this is the best we can do because we know this function doesn't have an antiderivative expressed in terms of elementary functions, but I think this is already pretty satisfying. And lastly, in case you're curious about the Bessel function, let me just give you some little fun facts just to end the day. So fun facts. As I said, the Bessel function is defined, of the first kind, is defined as this integral, 1 over pi, integral from 0 to pi, cosine of nx minus y, sine of x dx, where here is where the y appears. And why is this useful? Because it turns out Jn, if you want, of x, solves the following differential equation: x squared y double prime plus x y prime plus x squared minus 1 y equals 0. So not the same y here. If you let y be this, then it solves this differential equation. And then in case you don't really like this integral formulation, but you like the power series formulation, it turns out you can write this as this: the sum from m from 0 to infinity of minus 1 to the m, I think m factorial, m plus 1 factorial, x over 2 to the 2m plus 1. Which also says you can write this integral as like a double sum power series of this, which is also neat. And this is defined for integers, n. You may guess, you may ask, how do you define it for non-integers? And it's a really neat formula. So in general, if alpha is positive, if alpha is positive, or maybe, okay, alpha positive, and even if y is complex, as long as the real part of y is positive, then you define j alpha as follows: 1 over pi, integral from 0 to pi of cosine of alpha x minus y sine of x dx. So that is the generalization, okay, of that you would expect of the Bessel function. But it turns out if alpha is not an integer, or even if it is, you have to add the following very strange term: sine of pi alpha over pi. Notice, if alpha is an integer, this becomes 0, so usually irrelevant. But you add this weird integral from 0 to infinity, minus y sinh of x minus alpha x dx. Oh my God, who would have known that we have this extra term? And last but not least, why do I call it the first kind? There's also a Bessel function of the second kind, which is defined as follows. So the start is very similar. 1 over pi, integral from 0 to pi, sine of y, sine of x, minus nx dx. But then you have this other strange term, minus 1 over pi, integral from 0 to infinity, e of nx, plus minus 1 to the n, e of minus nx. Kind of like cosh or sinh, and e of minus y, sinh of x dx. But you see, first of all, not only it says the cosine. The first one is with cosine. This first kind is with cosine. The second kind is with sine. And you have this very strange term as well. And notice this is for n integers. Probably something different for alpha, any number. Alright, so I hope you like this impossible integral that was made possible. If you like this and you want to see more math, please make sure to subscribe to my channel and to ring on the notification bell. Thank you.